Hey everybody! So in this video we're going to be talking about exact differential equations. So let me first start this video by pointing out some really interesting implicitly defined curves. And that's where all this exact stuff is going to lead us to in the end. So let's start there and take a look at these. All right, so I've got a curve that y'all should recognize, right? X squared plus y squared equals 9. You know what this represents, right? This is a circle of radius 3, of course. But look at this curve. This is defined without solving for y, without solving for x. We just have an equation involving x and y. And just by having that equation, we can make sense of what the curve would look like, the set of points that satisfy that equation. And so this is an implicitly defined curve. Implicit means that you haven't necessarily solved for x or y. Explicitly defined would be that we did solve for x and y, but this is implicitly defined. Okay, let's take a look at some of these other ones. We've got an implicitly defined curve down here. What does that one look like? Some of these can look really interesting. Here we actually get a pair of wavy lines. All right, let's take a look at this next one. This implicitly defined curve is a curlicue. Let's take a look at this one. I like this one. You get this infinity symbol. Pretty cool. And this one is really wild. Take a look at this. We get a whole bunch of disjoint closed curves. Okay. Now, if you think about from multivariable calculus, if you think about these as functions of x and y and the fact that we're setting them equal to constants, these can be thought of as just level sets of a function of a graph in 3 dimensions. All right, so think about that and think you can make sense of these curves that way. But for us, we don't really need to go there. The point is we have a function of x and y equals a constant. Okay, so that's where I want to start in this section, thinking about that. So let me write that down. Okay, so we're looking at things that are of the form f of xy equals a constant. Oops, off the camera. All of these things are of that form. If you look at the first one, x squared plus y squared is a function of x and y, and I've got it equal to 9. Definitely of this form. Next one, that's a function of x and y equals a constant. All of these are like that. All right, all these examples were exactly one of those things. Okay, let's just take one of those examples and work with it a little bit more. Let me get out of the way here. So let's just take the simplest one there, x squared plus y squared equals 9. Okay, what I'm going to do to this is I'm going to make a differential equation out of this. How do you make a differential equation? Take a derivative. All right, so I can differentiate this implicitly, right? Differentiate it without solving for y. I'm going to differentiate everything with respect to x. So you know this from Calc 1. So look back in your Calc 1 notes, look up implicit differentiation, and implicitly differentiate this with respect to x. All right? Pause the video, and then we'll come back and check our work together. Okay? So go ahead and pause. 3, 2, 1. Okay, let's check our work. So when you differentiate this implicitly, what do you get? Well, the derivative of x squared with respect to x is, of course, 2x. The derivative of y squared with respect to x is 2y times dy dx. Now, where did that dy dx come from? Well, that's because we're thinking of y as a function of x. All right, so we have to use the chain rule here. You could think of doing the same thing here, but you'd get dx dx, but dx dx is just 1, right? So you don't need to write it down. And the derivative of 9 is 0. Okay, so we get this. Now I'm going to do something else. I'm going to multiply through by dx. So this is what you should have gotten when I asked you to implicitly differentiate. So if you got that, bravo. But now I'm going to do something extra. I'm going to multiply through by dx. Okay, so I get 2x dx plus 2y dy equals 0. Okay. Now, what did I do there? I split this dy dx apart. Now, you have to be very careful when you do that. And we shouldn't, you should be very cautious about how you interpret a statement like this. So for us in our class, we're just going to interpret this statement to mean this. All right, so when you see something like this, think, divide by the dx, put it back into this form. That's what we're talking about, because this is something that makes sense to us. We understand what this means, dy dx is a derivative. Pulling this apart, even though it looks like a fraction, we write it that way, you have to be really careful when you pull these apart. It's not something you should just do frivolously, okay? But we understand that this just means this. And what we have here now, then we understand that this is a differential equation. And this up here is the solution, all right? We haven't solved it for y, so it might look a little unsettling at first, but we do know that it completely defines a curve that we completely understand, and so it's a completely meaningful solution. So going from here to here is what we want to do. We want to start with a differential equation and come back to here. Even if we can't solve it for y, that's still okay. So this is what we're interested in doing in this section, going from the differential equation up to the implicitly defined curve. Okay? Now what I'm going to do is follow the same steps over here. Okay? What did we do? To get from here to here, notice that this guy is just the derivative of this function with respect to x, treating y as a constant. All right? That's not the case. You don't treat y as a constant in this step, but if you look going from here to here, that actually is what gets you this. All right? So if you differentiate this with respect to x treating y as a constant, you get this. So do the same thing here. That is the derivative of that function with respect to x. I'll write f subscript x to denote that. Dx. That's what this is. And then this guy is the derivative of this expression with respect to y, treating x as a constant. So that's just fy dy. And on the right-hand side, the derivative of c is, of course, 0. So what we did is we went from here to here. That's the same thing as going from here to here. And what we end up with here, is a function of x and y times dx plus a function of x and y times dy equals 0. And what we want to do, we want to start with something that looks like this and then see if we can get back to here. That's the goal of this section, is to start with something that looks like this and see if we can find this. And a differential equation of this form is called exact if such a function exists. All right, that's what it means to be exact. So m dx plus n dy, knowing that these are functions of x and y, is called, I see I'm going to be in the way in a second. Let me scoot up here. Woo! Is called exact if f of xy exists. So that, the partial of f with respect to x equals m, and the partial of f with respect to y equals n. Okay? And then we will have solved this differential equation. So that's the goal of this section. Okay? So let's take a look at some examples. Okay? So the first example that I want to look at is this one. We'll do 2/3 x to the negative 1/3 dx plus 2/3 y to the negative 1/3 dy equals 0. That is certainly something of this form, right? Okay, so can we find the function that this came from? Okay, well, we got to work that whole process backwards, right? So if you look at the function, the derivative of the function with respect to x was supposed to equal m, right? This is our m in front of, so the m is the thing in front of the dx, and that's supposed to be the derivative of f with respect to x. So to get back to f, what should we do to this? We should anti-differentiate it with respect to x, okay? So f should be the antiderivative of this thing with respect to x. So, but wait, let's look at something else. Fy is equal to n. The n is the thing in front of the dy. So this should be Fy. So on the other hand, f should be the antiderivative of this with respect to y, right? Because this is supposed to be the derivative of f with respect to y. So not only should f be this, but f should also be this. So in order for this to work, we need to verify that these come up, that these agree, right? If these don't agree, then this is hopeless. Okay, so let's go through this. The antiderivative of this thing, well, what is that? Well, of course, that's just x to the 2/3. Okay, plus a constant. Now, here's where you have to be a little bit careful. I could just write plus c, but if you think about it, I'm treating y as a constant here. I'm anti-differentiating with respect to, how did I get to this? I differentiated with respect to x, treating y as a constant. So I'm still thinking of y as a constant. So that means any function of y will still be a constant. So really, any constant could be represented as any function of y. That would be a constant. So if I differentiated this with respect to x, I would end up to here. And so this is a valid antiderivative. Now let's do the same thing down here. I get, with respect to y, I get y to the 2/3. And now any function of x is a constant. Okay, so notice if I didn't write those down, it'd be hopeless. These things are supposed to agree, right? And look, they don't. However, because with this one, we're allowed to have any function of y here, well, that can accommodate that. This is the function of y that we're talking about here. And this h of x can accommodate the x to the 2/3. That's the function of x that I was talking about here. And so I can see what my function is. My function has to be x to the 2/3 plus, what's g of y? It's this, y to the 2/3. Or equivalently, y to the 2/3 plus this, which is x to the 2/3. Either way, I see what my function is. My function is x to the 2/3 plus y to the 2/3. Okay? And so the solution to this differential equation, remember what we started from, was the function equals a constant. Okay? So what I end up with is x to the 2/3 plus y to the 2/3 equals a constant. And that is the solution to that differential equation. The fact that these agree and that I can match them up is telling us that this differential equation is exact. Okay, it exactly came from, one way to think about it is that it came from some expression like this. Okay, now one thing you might be thinking about is like, I could have also put, this could have had a plus c in it too. It doesn't have to just be purely a function of y. And this could have its own plus c, maybe a c1 over here and a c2 over here. Yeah, you could introduce those, but it's not going to matter because when you set them equal to a constant, you could just subtract them off. And then when you subtract all those constants together, you end up with a new constant, so we're just calling that c. Okay? So you don't need to think about those extra constants when you do this because we're going to have a constant on the right anyway. Okay? So let's look at another example. Well, we'll go to a new sheet. Okay, so this next one, what we're going to do is we're going to start with 2xy cubed dx plus 3x squared y squared dy equals 0. Okay? And we want to go through the same steps. So I'd like you to try doing the same thing. Okay? And let's compare our work when we're done. All right? So Let's pause the video. 3, 2, 1. Okay, we're back. Excuse the noise. It sounds like somebody's moving in out back. So what we're going to do is we realize that this is the term in front of the dx, so it should be the derivative of f with respect to x, right? So to get f, what I'm going to do is I'm going to anti-differentiate that with respect to x. But at the same time, this is supposed to be the derivative of f with respect to y. So at the same time, f should be the integral of that dy. Okay, so let's see what we get. Well, thinking of y as a constant here, all right? So the antiderivative with respect to x is just x squared y cubed plus some function of y. And what's this one? It looks like x squared y cubed. I'm treating x as a constant, right? Plus some function of x. Now here it's a little bit different. I can't match this function here with this because this is not just a function of y, right? So this is not g of y. So I can't just draw that arrow and say, well, this is that. And I can't just draw an arrow and say this is that, right? Because this is not just a function of x. So it's a little bit different than before. But all we need to do is we need to find functions g and h so that these are the same. And I definitely can, right? I can just take g and h to both be 0, right? If this is 0 and this is 0, then these agree. So it works. F is just this function, right? So in this case, the function is just x squared y cubed. And so my answer to the solution to the differential equation is just this. All right, so sometimes these functions will accommodate the other term, but sometimes you don't need them to. Sometimes it works out just fine without them, right? You just have to figure out what those things are, right? Okay, let's do another one. Okay, so the last example is as follows. So we're going to have y plus 1 dx plus, what was it here, 2x dy equals 0. Okay, go ahead and do this one on your own, and then we'll check our work together. Okay, and prepare for a little surprise here. So 3, 2, 1. Okay, let's check our work. So we know that this has to be the derivative with respect to x. And this has to be the derivative with respect to y. So to find f, I'll anti-differentiate it. Okay, let's go through. All right, the antiderivative of this. Well, that's just going to be y plus 1 times x plus some function of y. All right, and this is going to be x squared plus some function of x. Okay, and now here's where you may have had a hard time, right? How are these going to be equal? Well, I need the g of y to accommodate what's not up here. But one of the things that's not up here is the x squared. I can't accommodate x squared with g of y because g of y is a function of y, not x. So I'm in trouble. This can't work. And similarly, if I look down here, what's missing in this expression? Well, I've got a y times x and a 1 times x. Okay, well, this can take care of the 1 times x. Like, that's a function of x. But it can't take care of the y times x. That's a function of x and y. And this is just a function of x. So this can't accommodate that. So it's not possible to find these functions. So this is a situation where it's not possible to do it. If there were to be a function, it would have to agree with both of these. But these, we just said, these can't be simultaneously true. And so what we get is no f of xy exists. Okay, the differential equation is not exact. move out of the way so I can write this down. All right, so that's an important example because this can happen, right? So what we're going to talk about in the next video is how can we tell ahead of time when it's going to be exact, all right, so that we don't have to just go through this and fumble through it to find out that, whoop, it's not going to work. And turns out there's a theorem that we can use to check very quickly at the beginning whether a differential equation is exact or not. And so we'll take a look at that theorem in the next video. So I'll see you there.